We can get started now. Good afternoon. The Learn Smart module for Chapter 7 is going to go through Tuesday evening, so you have the whole weekend to do that. And I want to remind you one last time that Monday we won't have class here. Look for a video. Hopefully by tomorrow morning or tonight I'll actually have it up, so if you want to watch it early. And then watch it over and over again. You can do that. Let's see. We're talking about stereochemistry. I plan to go, well, we'll see how far we get today. The Monday's video will probably finish off Chapter 7. And then when we come back on Wednesday, we'll be beginning Chapter 8. So that's my plan. So let's talk about this a little bit. We were discussing about chiral molecules and the fact that we have stereoisomers, which are related as mirror images. Right? Those are, what do we call those? Enantiomers. We also have stereoisomers, which are not related as mirror images. And what do we call that relationship? Diastereomers. Very good. We have carbons, which are asymmetric or stereogenic, and if we have carbons that have 4 different groups attached, that tetrahedral structure means that that is a center of asymmetry. And we have specific rules for designating that as either an S or an R. We went through a number of that last week. If you still have trouble doing that, go through your book and do problems and look at the solutions manual and see that you're doing it right. Because it is critical to be able to look at molecules written in all different ways to see what the stereochemistry is. We talked briefly, and I'm going to spend a little more time today going through this as well, that when we carry out chemical reactions, we can actually create centers of chirality or stereogenic carbons. In this case, the example we looked at on Wednesday was the addition of HBr to a double bond, which initially is flat. So this carbon is sp2 hybridized, right? So there is no mirror image isomer possible there at that carbon because that carbon actually has a plane of symmetry right through it. Once you then generate a tetrahedral carbon, sp3 hybridized carbon, with another group, now you have a possibility of having 4 different groups attached. You can generate different mirror images. And the only way to control the formation selectively of one mirror image over the other is to have what present? You have to somehow have something else that's chiral and optically pure that is not a 50-50 mixture to influence that. And so in the case where we have this carbocation, there's no difference between adding that bromide from the top or the bottom of that carbocation. Okay? That's the actual bond forming which would generate one mirror image or the other. So only if you have somehow other chirality in the molecule, or actually in chemistry we often use chiral catalysts or other chiral environments to help that. You have to somehow make the energy for the transition state energy for the addition of the bromide to the top different than the bottom, for example, if you want to get selectivity for one over the other. So we have to have some other chirality present. Otherwise, the transition state energies in something like that have to be equal. There's no difference. Diastereomers. We talked about diastereomers, and there are 2 kinds of diastereomers, right? We talked about diastereomers, which are that are cis and trans diastereomers, and diastereomers which are configurational. We're going to focus a little more on that today. So enantiomers, again, mirror image isomers. Diastereomers, they are stereoisomers, but if they aren't exact mirror images, then they can't be enantiomers. Everything else falls under that category. Oh yeah, here they are. Cis and trans is an example, right? Whether that's a double bond or whether that's on a ring like a cyclohexane or a cyclopentane, those are diastereomers. Okay, and that leads us to continuing our discussion of configurational diastereomers. We talked about this example of tartaric acid, which happens to be a symmetric molecule, right? tartaric acid has 2 stereocenters. And I want to point out that this is symmetric. The way I've drawn it in this sort of, not in the fully extended open chain, but in this form, you can see that this group is identical to this group is identical to this group is identical to this group, etc. But the configurations are opposite. Okay? One way to easily see whether you have situations which could be more complicated is this group, is the molecule symmetric? So if you think about this, could you figure out that numbering one way from one end to the other would be different than the other end? So in this case, if I started numbering 1 here, 2, 3, 4, would that be different than numbering from this side, 1, 2, 3, 4, if you were to try to name that? No, it'd be the same. That molecule could be numbered, and you get exactly the same numbers for the groups from either direction. So that tells you that this molecule has some symmetry to it with regards to, not in the chiral sense, but in the groups being equal on either end. So anyway, if you take a look at the actual configurations of that and its mirror image, what you see is that we have exactly opposite. Okay? Another way to look for enantiomers and diastereomers is to look at all the different configurations for all the stereocenters and see if all of them change. Then you know they're enantiomers or mirror images. Okay, so those two are mirror images. We have the S configuration. Here's the S configuration. If you take the mirror image, both of them should be opposite, right? And that's exactly what we have. R configuration and the R configuration. So if I draw that, I just showed it sort of the mirror image, but if I draw this in the same sort of way, okay, you can see, let's see here. So if I flip, I'm flipping this one over, so that would go down, and this one would be up, right? If I just took this and flipped it over, oops, I got my oxygen. There you go. So you can see that we have switched both of these configurations. Up now becomes down, down becomes up. Okay? But if we take this molecule and switch only one of those centers, leave the other one the same, now we have a different stereoisomer, which is different than either one of those, and those are related as diastereomers. So this pair of molecules, those would be diastereomers, and that pair of molecules would be diastereomers. And a couple of other things that would clue you in to recognizing that is to look at the specific configurations of the stereocenters. So we have S here, and that is S here. That didn't change. Okay? The S here becomes R here. That changed. Okay, so we have a situation where we have 2 stereocenters in the molecule, one changed and one different. So they obviously can't be mirror images. So they must be a diastereomer. Okay, any questions on that so far? Understanding those relationships? Okay, this molecule now, I want to take a closer look at this molecule. If we were to take this molecule and look at its mirror image, what is the relationship there? Okay? This shows an interesting, unique situation. When you have a molecule which has the same groups along the chain, a carboxylic acid, a COH, COH, carboxylic acid. Again, if you have a situation where you could number the molecule from either direction, and it would be the same thing in terms of naming the molecule, its mirror image actually is going to be identical. This is a special case which we refer to as a molecule which is meso. Meso is a term we use to represent molecules which actually have asymmetric carbons, that is, carbons that are stereogenic or chiral carbons, but overall the molecule has a plane of symmetry, so its mirror image actually happens to be identical. So these actually are not the same molecule. I mean, these are the same molecule exactly, even though it's a mirror image. And we can see that a molecule that would have a plane of symmetry in it should be the same as its mirror image. And in fact, if you were to bisect this molecule with a plane right through here, okay? Think about this as a mirror plane going forward and back, okay? That molecule is reflected exactly the same on the top and the bottom. So within the molecule, it's a very symmetric molecule. Even though we have stereocenters in it that have configurations, okay? A clue that you might possibly have a meso compound, a molecule which is achiral or not chiral because of the mirror plane of symmetry, even though it has stereocenters, is that within the molecule you have two configurations which are opposite. So notice this one is S and this one is R. So if I were to, for example, number this molecule 1, 2, 3, 4, and within the name of this molecule, this would be, I would use as a prefix to this 2S, 3R as a prefix to the name of that molecule, right? Well, the mirror image, look at the mirror image of this molecule. If you take the mirror image of this particular stereocenter would flip from S to R, and this stereocenter would flip from R to S. Okay? But since the molecule has higher symmetry, we could actually name it exactly the same because all the groups are identical, and I could number it 1, 2, 3, 4 like that, and I would still have 2S, 3R. Okay, do you see that? See how you can actually, without even visualizing everything, if you know the configurations, you can look at some of these comparisons and see. So identical molecule, and in fact, if you think about taking these molecules and superimposing them, okay, take this molecule on the right and simply leave it on the plane of the board and simply rotate it 180 degrees and slide it over, everything would line up the same, right? Have to be the same. Okay, what if instead of this, now I do something like, I have a molecule like this. Instead of an OH here, I have a chlorine. What's the relationship between these molecules? What have I done to the molecule now? I've removed any plane of symmetry from the molecule because no longer is there a plane of symmetry in this direction because the chlorine and the OH aren't the same. It's not reflected from top to bottom. Okay? Now, I no longer have a molecule whose mirror image is the same. These are now enantiomers. Because the molecule is not the same in either direction. Here, if I number this way, it'd be 2-chloro, 3-hydroxy, and if I number it this way, it'd be 2-hydroxy, 3-chloro. That's no longer the same, okay, because it's not identical. Now we have enantiomers mirror images. And again, if you use all the things we look at, the center with the chlorine, S, has become R, right? If you rotate this 180 degrees and slide it over, the OH group is up here, and the chlorine is down here. It doesn't superimpose. So be really careful about seeing these issues of symmetric molecules or non-symmetric molecules when you're thinking about their relationships. Okay, so that's another compound, or another term to put in your vocabulary, meso compounds. Okay. Well, we can talk a little bit about the properties of molecules. If you remember when we were discussing the mirror image isomers and enantiomers, I told you that the physical properties are identical except for how those molecules interact with plane polarized light. It'll rotate light in one direction or the other, by the same amount though. Okay, so if you take a look at these derivatives or these isomers of tartaric acid that we've been talking about, What I have here is the tartaric acid with SS configuration. Here it's RR configuration. And here is the SR configuration. This one is the one which is symmetric in meso. The relationship between this and this is a diastereomer. The relationship between the bottom one and the top one is a diastereomer. The relationship between these two are mirror images, the top two, right? So those are the three possible stereoisomers for tartaric acid. And notice some of these physical properties. The density of the molecule, exactly the same for the mirror image isomers in enantiomers, 1.7598. But the other isomer, which has a diastereomeric relationship with those, has a different density. Okay, diastereomers can have different physical properties that we can measure more easily. Melting points. Enantiomers will have identical melting points. The diastereomer could have a different melting point. In this case, it is lower for that one. Optical rotation. This one is 0 because it's not chiral. It's not chiral, so they can't have any rotation. The mirror image isomers have the same amount of rotation, just different directions. That's what that sign means, the plus or the minus. Is referring to the rotation of that light in one direction or the other. So, you can see now that physical properties can be different of stereoisomers which are related with diastereomers. So, I just want to throw this out because we'll talk about it in a little more detail later. If you wanted to somehow separate, let's say you have a 50-50 mixture of enantiomers. You do that HBr reaction to make 2-bromopentane. And you have a 50-50 mixture of enantiomers. How do you separate them physically? How do you separate any substance? You have to have some kind of interaction with other matter which interacts differently with those substances, right? So if you have a molecule whose physical properties are essentially the same melting point, the same density, these will have the same solubility in different solvents. You can't separate them based on physical properties. You can't isolate those molecules. However, you could isolate one of these from one of these because they do have different melting points. They would potentially, if they're liquid materials, they would have different boiling points, different densities, different solubilities. There you can think about designing some way to physically separate a mixture of diastereomers. But you can't physically separate a mixture of enantiomers. Okay? So given that, let's get back to my question. How would you separate a mixture of enantiomers? You have to somehow convert that into a mixture of diastereomers and separate it and then get back your enantiomer. And we'll talk about that. There are some ways in which we can do that. It's not easy, but it is possible. And we'll talk about that in a little bit. I just want to show a few more examples of molecules and their three-dimensional structures and their shapes, and talk about what the properties we observe versus what we have. So let me pull this up. So let me just take a look at cyclohexane for a moment. Okay. I showed you that cyclohexane. Let's say if we have the 1,4-dimethyl cyclohexane, right? We could have the cis isomer. We could have its diastereomer. Okay. The trans isomer. Okay. And then if you take the cis or the trans, and you look at their mirror images, are they different? Are they different? You should say no, because the slide I had previously showing cis and trans diastereomers, these have to be examples of achiral ones. And again, if you look at, there's a plane of symmetry bisecting the molecule there, and there's a plane of symmetry bisecting this molecule here. Okay, so if you can draw that on even showing this flat representation, you can see that plane of symmetry. But we know cyclohexane is not flat, right? What's the structure, three-dimensional structure of a cyclohexane? What's the conformation? It's a chair conformation is the most stable one, right? So if we take a look at a chair structure, okay, and we have a CH3 group, I'm going to draw it out here for you, a CH3 group up, and then 4 carbons away we have a CH3 group up. Okay, that's the cis isomer. Even within this structure, and remember this part of the molecule is closer to you looking at a side-on view, okay, in 3 dimensions. You could still bisect the molecule. Let me see if I can draw a plane here. I'm not very good at the 3 dimensions. Okay, if you bisect the molecule right down the middle of the molecule, you can see that you can slice it in half and have the left half be a reflection of the right half, right? So that plane of symmetry is still there in the molecule. You can see that. If you look at this molecule, we have one CH3 group axial and one CH3 group equatorial. And unless there's a large energy difference between the groups, in this case they're both CH3s, both of these conformations are probably existing equally. The energies should be the same. So if I look at the ring flip isomer, yeah, all these things we talked about in the previous chapters come back to haunt you, right? Okay, that's the other ring flip isomer, and it has the same symmetry properties. There's a plane of symmetry still bisecting the middle of the molecule. So again, this is achiral. And the trans isomer, I'm not going to draw both of these, but I'll just draw one. It's also the same, even though these are not equal. Like I said, we'll draw both really quickly. The trans isomer has 2 ring flip isomers. Okay. And both of these, still, even though it favors this one on the right, it's more stable. We talked all about that in the previous chapters. Even though that one's more stable, you still have a plane of symmetry bisecting it. Okay, actually both of those. So mirror image has to be identical. These are achiral molecules. Okay, you're following me so far? All right. What about the molecule? I'm gonna erase this, so hopefully you've gotten this written down if you're writing it down, or you can go back and look at the video. What about the molecule which is similar but has 1,2 dimethyl cyclohexane? Okay. What are the relationships here for these molecules? The cis 1,2 dimethyl and the trans 1,2 dimethyl. Okay. Let's take a look at their mirror images. Okay, that's the mirror image for the cis isomer. What's the relationship between those 2 molecules? Meso. This is a meso compound. It has stereo, it has configuration centers, but there's a plane of symmetry, and if you rotate this around, it'll line up again. Yes, meso. Why wasn't the 1,4, why wouldn't we call the 1,4 cyclohexane meso? Were there centers of chirality in the 1,4 stereoisomer? Or the 1,4 molecule? See, it really takes some looking at these molecules closely. Let me just draw this for a second. 1, 4, doesn't matter if cis or trans, I'll just draw the cis, right? So let's take a look at the carbons, which we have potential stereogenic centers. Okay? Are there 4 different groups attached to those carbons? No. No. Notice, this way around the ring is identical to this way around the ring. Because there's a plane of symmetry bisecting through the carbons of the ring. Okay? So those carbons are not asymmetric centers. They're not stereogenic centers. Okay, do you see that? However, in the top case, when we have 1, 2, now, let me just get rid of this one. Now we have carbons which are stereogenic centers. So let's take a look at this carbon. I'll write the hydrogen there. That carbon has 4 different groups attached because the CH3 is different than the hydrogen, which is different than the CH2, which is different than that carbon. Each of the 4 groups attached are different. And the same thing if you take a close look at the other carbon. So there are 2 stereogenic centers. That's why, but because the molecule has another plane of symmetry, and notice that plane of symmetry is bisecting through bonds, it's not actually bisecting specific atoms in the ring. It has a mirror image. The mirror image is an identical molecule, and it's a meso compound because it has stereo centers, but is achiral because it's meso, because its mirror image is different. Okay? So you follow all that, and there are those subtleties. What about the trans isomer? What can you tell me about the trans isomer here? Yes, the trans isomer, these are, I'll draw the mirror image. These are enantiomers. Okay? There's no plane of symmetry in the molecule. If I bisect the molecule this way, right? CH3 coming out on the top is reflected by a hydrogen in the bottom, and a CH3 in the bottom on the back is reflected by a hydrogen in the top. And again, if you take the molecule on the right and rotate it 180 degrees and slide it over, okay, the CH3 which is down rotates up to this position, and the CH3 which is up will rotate to this position, so they won't overlap. Okay, so those are enantiomers. Just by moving the CH3 group around the ring, we can have the ring exactly symmetrically substituted in the case of 1, 4. But now we have a case where it's 1, 2 that's substituted. This is the same kind of situation as we talked about with tartaric acid. We could have a meso compound because of the plane of symmetry in the molecule. Okay, and another way to look at this again is to look at the specific configurations S and R. So let me see if I can't clean some of this up here. Okay, so let's look at the configurations in the top case. S and R configurations for those. So if we look at this carbon on the top first, what is the R or S configuration for that carbon? What's the highest priority group? Well, this is going to be the highest priority group, right? So it's carbon, carbon, carbon. Okay, so let me just slow down. Carbon, 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 and hydrogen. Hydrogen is the lowest priority. It's pointing back. Okay. This is a CH3. This is a CH2. And this is a C bonded to 2 other carbons. Okay? So this is going to have highest priority. This is going to have next highest priority. This is going to have third highest priority. Right? So the configuration for that is going to be R. So here it's R. And then I'll do this a little more quickly. This is also, and this one is S. Okay? If you reflect that, this one is S. And this one is R. But again, because we could number the molecule from either direction, because it's symmetric, it's the same. All right. This one, on the other hand, is going to be RR, and it's reflected as SS. Clearly, they can't be meso because you don't have that RS situation like we have at the top, just like we saw with tartaric acid. Okay. Now, let me make it just a little bit more complicated, because I know how much you like to see complicated things. I'm going to draw that cis isomer again. Let's say cis 1,2 cyclohexane, which we already just determined is a meso compound. Okay. What about the chair structure? Okay. Chair structure, and again, I'm just going to choose, let's see, let's just choose this carbon. Actually, maybe I'll just use the carbons that are pointed in front of us. So here's a CH3 up, and the hydrogen is equatorial. And on the carbon, it might help if I label these as well. The red carbons here are right here. Okay? That CH3 group is up, and the other CH3 group is also up, and there are two positions, axial and equatorial. Okay? If you look at the chair structure, is there a plane of symmetry? It's a 50-50 possibility for a correct answer. Is there a plane of symmetry? No. No. There's no plane of symmetry. Right? If you actually look at the three-dimensional structure of cyclohexane, there's no plane of symmetry like we can easily see if we draw it flat. Right? We can bisect between those two CH3 groups. We can bisect. Well, if you bisect a plane, through the molecule here, that CH3 group, I don't see it over there. Why do we see meso properties for this molecule? Because we have looked at one frozen conformation, okay, and we know this molecule is undergoing very rapid green flips, okay. Oops, yeah, CH3. So very rapid ring flips, okay? Those have identical energies, and even if they didn't have identical energies, at room temperature they would most likely be flipping very fast anyway. So as a consequence, what we actually are observing in terms of the property of this molecule is the average of these, which is the kind of flat structure. So these are rapidly equilibrating. Although, for all intents and purposes, a frozen conformation might exhibit asymmetry or be a chiral. What we observe when something is just rapidly moving around very fast is the average of that. And actually, if you take a look at this, another way to think about this, these two conformations are mirror images of each other. So in a sense, maybe another way to think about this being an achiral molecule is that we have very rapidly interconverting enantiomers. So we always have a racemic mixture, or always a 50-50 mixture. Well, but in reality, of course, the molecule is moving, so it's not stuck in these figures. The good news is, although this probably creates some confusion and more complication to this whole picture, the good news is when we look at ring structures, when we think about symmetry and chirality and meso and things like that, we can just use these flat structures and look at them and see, because it is a reflection of what that average conformational changes are. Okay, so that's the good news. You have an easy way to see it. Okay, any questions on that? Hopefully you're still thinking more and more and more about visualizing three-dimensional structure, because this is all related. Okay, so let's just look overall at a large overview of what we call isomers. Isomers are molecules different molecules which have the same number and kind of atoms, but somehow they're different. That's a very general categorization in isomer. And now we know we have lots of different kinds of isomers. If those atoms are bonded differently to each other, we've actually moved atoms from one place to another and bonded it to different atoms, that's a constitutional isomer. That's like normal butane and isobutane, right? Or 2-methylpropane. Those are constitutional isomers. Stereoisomers have all the same atoms bonded to the same atoms, but they're arranged differently and fixed in space differently so that they can't interconvert. Like the conformations for cyclohexane rapidly interconvert, so we would consider those equivalent, right? These are fixed in space. But we have also different kinds. Diastereomers, which are not mirror images of each other. Enantiomers, which are mirror images of each other. And within the class of diastereomers, some of those are chiral or configurational, depending on differences in the specific stereocenters. And some are simply cis and trans based on double bond or ring restricting the molecule's motions. Okay? 4 configurational compounds. Actually, if you think about it, we've given examples where we have 2 stereogenic carbons. So it's pretty easy to see with tartaric acid or with the dimethyl cyclohexane. You can easily see we have RR, RS. And if you think about a molecule with 2 stereocenters, it's easy to tell what the maximum total number of different stereoisomers might be possible, right? You just raise 2 to the power of the number of stereocenters. So if you have one one chiral center in a molecule, the only thing you could have is, like, let's say you have one stereocenter which is R, and then its mirror image is S. There's no other possibilities for arrangements. So you have 1 to the power of, 2 to the power of 1. That's 2, right? 2 possible stereoisomers. Well, if you have 2 stereocenters, like in dimethyl cyclohexane or tartaric acid, the maximum possible number of stereoisomers is 2 to the power 2, because of 2 configurations, 2 stereocenters. Can you do that math? 2 to the power of 2? 4, right? 2 squared is 4. There's a possibility for 4 different stereoisomers. It happens that one of them is meso, so its mirror image happens to be identical. So in actuality, in some cases it's less than that. In case of tartaric acid, it's 3. All right. If you have 3 stereocenters in a molecule, 2 to the power 3, right? You have 8 different stereoisomers possible. Okay. Again, it doesn't mean that all of them, some of those within there could be meso with their mirror images. So you could have less than that, but that would be the maximum number. So you can see, since this is 2 to the power of the number of stereoisomers, the more stereocenters you have in your molecule, the more possible stereoisomers at an exponential rate could occur. Okay, so glucose. Glucose, how many, if you remember the structure of glucose, how many stereocenters were in glucose? Remember glucose? I'm not drawing all the up and down. This is a basic sugar. Okay. 1, 2, 3, 4, 5. Those aren't oxygens, those are circles. 5 carbons, which are centers of chirality. So 2 to the power of 5. That's a heck of a lot of different isomers for sugars. And that's why glucose is just one particular isomer. And there are a number of other possible isomers, which some of them are different sugars and with names and things like that. So it gets complicated. And so remember on one of the first days of class I said organic chemistry is the chemistry of carbon compounds. And in theory, you could have an infinite number of carbon compounds because you could just link more carbons and branch them, right? And our systematic naming should allow you to name each one of those infinite numbers. Well, multiply that now by the number of stereocenters to the 2 to the power of that, and you can see you have a lot more than an infinite number of molecules, if there is such a thing. Okay, one thing I want to point out, I'm not going to dwell on this. Your book talks about another way to represent the stereochemistry, Fisher projections. This is an older way to do it, but if you're taking PCATs and MCATs and tests like that, sometimes they still show these on there. So I want you to be aware that sometimes molecule stereochemistry is represented just by a cross, like that molecule here on the right. They don't show bold or dashed. It's assumed when it's written as a Fisher projection. I don't like it because it's ambiguous and it assumes you know, but you might encounter this. So I want you to see it. I'm not going to have you know this for the class, and I'm never going to represent molecules this way, okay, because I hate it. But when you see this, a Fisher projection where you have a cross, what that means is that there's a carbon in the center, and then you have those 4 groups, and it's assumed that the groups that are going to the sides, left and right, are coming towards you in that tetrahedral carbon. So they're both coming towards you. And the groups that are up and down are going back away from you. Okay, that's assumed. So if you need to know that for anything in the future, that's what that is representing. You can see a better picture of it here. These are rather simple molecules. Sometimes you'll see, especially if you look at biochemistry texts and other books like that, if you have more than one stereocenter, that's why it gets a little more confusing. If you have one stereocenter, it's pretty easy to do, but if you have more than one stereocenter, like sugars, you might have something like this. Okay, each one of those crosses is representing a carbon with a particular configuration. Okay, so you might see a sugar in its open chain form written like that. Not showing any bolded dash. You have to assume. So again, with that, with a Fisher projection, you are assuming that these groups are coming towards us. So if I make it bold, and then that's going away, that's going away at that stereocenter. Same thing for that one, and same thing for that one. Okay? It doesn't really represent well the actual picture if you were to draw it like this. That wouldn't really represent this well. But that's what people have used for indicating those in the past, and I'm sure you'll see it somewhere along the way. Okay? So I don't want to spend any more time on Fisher projections. I will never use them. Okay, I want to come back and spend the last 8 minutes or so and talk a little bit more about reactions. We talked about the fact that if you have a reaction like this, which produces a stereocenter, you can produce a 50-50 mixture of enantiomers. We've generated a new chiral center, but that we don't have any way to control the formation of one over the other. Okay? Some reactions, however, are stereospecific. Even if we can't control which enantiomer or which mirror image we produce above the other, there are reactions which influence the formation of one diastereomer over another. Remember, diastereomers have different properties. The transition states leading to diastereomers have different energies, and so in principle you could have selectivity. And in this case, this reaction which we talked about, adding bromine, Br2, to a double bond, in the case of cyclopentene, right? We know that gives selectively a trans compound. That's what we would refer to as a diastereoselective reaction. Or actually, in this case, it's what would be a stereospecific, a diastereospecific reaction, because we only get one. And that's because of the nature of the mechanism. We form a bridge bromonium, so now what we have is a situation where we have that planar sp2 double bond. We form this intermediate where the top is blocked. Okay, energy to bring the bromide from the top would be much higher than bringing the bromide from the bottom. So we will always get the trans compound. What we don't have here is the ability to change the energy of adding to the left side of this from where I've shown it or adding to the right side. Okay? If we add this, oh, I should have put this the other way. If this bromine adds with the left arrow, you'll get this compound to the right, right? Bromine down here, bromine up there. And if the bromide follows this right arrow and breaks that bond, that bromine shifts over and we have the bromine up on the left and the bromine down on the right. Those are equal energy pathways. These are mirror image isomers. These are enantiomers. So we have a selectivity in the reaction to form one diastereomer. That is, we don't form the molecule with both of those bromines up. Okay, that's not formed, the cis isomer. But still, we have no way to control the formation of one stereoisomer, one enantiomer over the other. It's 50-50. Okay? If, however, well, let me just talk about this. It's the same case if that double bond is not in a ring. Now, we don't see any difference in cis and trans here, because once you break the double bond, you have free rotation around that double bond. So you could draw this in two different ways. Okay? If we start with the cis-2-butene, it's stereospecific in that the bromonium ion forms this intermediate. Okay? Those are the CH3 groups in the back and hydrogens in the front. Okay? We still have the bromide coming from the bottom. It could attack on this side or this side. That would lead to the formation of this one and this one. These are enantiomers. Okay? We don't see any possibility of attacking here, or we can't notice it here because that bond rotates freely. If you rotate that bond, that bromine moves up on the top here. And notice, SS and RR for the enantiomers, SS and RR, if you look at the configuration, showing that 4-carbon chain just listed a different way. Again, 50-50 mixture of enantiomers. We can't really tell without that ring that it's stereospecific in terms of a cis or trans addition or syn or anti addition. The trans isomer will give the same compounds, but initially it's a different way. Initially, that double bond would have the CH3 going back, the bromonium ion, and the CH3 coming towards us. Sorry, my writing's terrible. Okay? We still see the same a different bromonium intermediate now because the CH3 group's different place. But again, we attack in both ways and we would get the RR and the SS. Okay? And again, we could draw it this way or we could draw it this way, identical. Okay? But keep in mind, the mechanism is still the same. We observe diastereoselectivity if that double bond is in a ring. If we have other chirality, now here is where we can really make a difference. If there's other chirality already in the molecule, in this case we have a stereocenter which has the S configuration, CH3 down. Now we have a difference. Actually, that CH3 group will influence both steps of this reaction. Okay? For example, the bromine could add to the top side of that ring, as shown here, or the bottom side of that ring. Notice that that bromine has to come from the bottom. It comes close to that CH3. Now there's a different steric environment. Okay? So we would get less of this one, and we would get more of this one. That's a stereoselective process. So we could form one diastereomeric intermediate over the other in the first step. And then in the second step, we also have a difference. So let's say we look at this one. We form this intermediate. We could add to the right side bromine down on the right and bromine up on the left to give this product. Or if the bromide adds here, it would give this product. But if that bromine has to come from the left, it's again coming close to that other group. And you can see here, there would be more steric crowding. So again, this would be formed less, and this would be the major product. Okay? That's how we can get some stereoselectivity in the generation of those new stereocenters if you have other chirality present to control that. Okay? I'm going to continue talking about this and finish up chapter 7. Please watch the video. Have a good weekend. We'll see you back here next Wednesday.